Welcome to the Section 5.5 video lecture. I am once again Dr. Scott Spaniel, your instructor for statistics. Welcome back. So far in Chapter 5, we've been talking about different ways to calculate different types of probabilities. And one really important part of calculating probabilities is knowing how many ways something can happen. And so what we're going to do in order to do more detailed probabilities is we need to talk about how do we count up how many ways there are to do something. And so that's what this section is mostly all about. Section 5.5 is all about different counting techniques. So what you should do now is go ahead and take out your notes for section 5.5. We're starting on page 25, and you can follow along. As always with these, those notes can be found either on Blackboard in this week's folder or on my math lab. So the first and probably most basic and most important rule of counting things is the multiplication rule. So if a task consists of a sequence of choices in which there are P selections for the first choice and Q selections for the second choice and R selections for the third choice and so on, then the task of making these selections can be done in P times Q times R times ... number of ways. So you simply multiply them together. So, for example, if a man has 6 shirts and 4 ties, and assuming they all match, how many different shirt-tie combinations can he wear? Well, it would simply be 6 times 4, which is 24. Okay, so that's the idea there. So if you want to pause the video and try the next one now, you could. And when you hit play, we'll go through it together. Okay, so similarly, if a woman has 5 blouses and 3 skirts, assuming they all match, how many outfits can she make? She just has 5 times 3, which is 15 outfits. So that's the basic idea of how to make these choices, is to figure out how many ways there are to make each choice and then multiply those together to get the total number of options. Now, there is some more math that goes into this. So if n is greater than or equal to 0 as an integer, then the factorial, n with an exclamation point after, is defined as follows. N factorial equals n times n minus 1 times n minus 2 times ... times 3 times 2 times 1. So you take the integer and you multiply it by all the integers that are smaller than it. And a couple of so for example here, 5 factorial would be 5 times 4 times 3 times 2 times 1. Okay. And we have, if we go to our Class Calc website, I'll show you where this is in your calculator. So on Class Calc, we can look at where this is located, hopefully, if it doesn't take too long to load. Okay, well, this is being kind of slow, so let's go and do this one by hand. So 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is 120. So 5 factorial would be 120. Okay. So similarly, to do 10 factorial, we just do 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And this is a good example of a time when using the calculator is going to be a lot more effective. So, for example, okay, so it's hopefully going to load here, right? Because that's a fairly long calculation to write out. So if we type in, I'm in the scientific calculator here, you just type in your number. And then if you go to algebra, nope, it's actually under stat, basic, and you've got your exclamation point right here. So you can add that, and then it tells me that that is indeed 3,628,800. Okay, here's what we got for that. And so the factorial is a very powerful thing. Now, a couple of special cases for factorials. 1 factorial is probably pretty straightforward. That's just 1. But 0 factorial is also 1. Okay, and that really goes back to the idea that we're doing multiplication here, and the multiplicative identity is 1. So that's why those are both 1. So an example of when you might use this are the following. Okay, so some examples of when you might use this could be, how many ways can 15 students be lined up? Well, how many choices do you have for the first student in the line? Well, for the first student, there are 15 options. But then for the second student, you've already picked one, so there's only 14 options left. And then for the next one, there'd be 13 options, and then 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and finally, you have that last student who goes at the end of the line. And notice that is 15 factorial. So if you have a number of things that you want to put in order, you simply take the number of things factorial, and that will tell you how many different ways there are to put them in order. So in this case, 15 factorial is, and let me bring this, actually, I did it on my phone, but let's bring it on here so I can point and stuff. So 15 factorial, in fact, you can just type in, is 1.3076 times 10 to the 12th power. So that's scientific notation, right? Which is something hopefully we've all ran into before. So it's 1.308 times 10 to the 12th power. And there's more decimals, but I decided to just round it off so that it looks like this. Okay. And so all that really means, right, is 1308, and then we have 12 decimal places. So 3 is a decimal, so 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So written all the way out, that would be what? Million, billion, trillion. 1,308,000,000,000 different ways to line up these 15 students. So there are a lot of options, okay, in order to line up these 15 students. So that's the idea. So if you want, you can pause the video here and try doing this other one. Okay. So Dan wants to burn a CD that will contain 12 songs. How many ways can Dan arrange the 12 songs? Well, you could have 12 for the first spot, and then he's already picked one, so now he has 11 left. 10, 9, 8, right? 7 choices, and then 6, and then he has 5 left to choose from, 4 left to choose from, 3 left to choose from, 2 left to choose from, and then the last one. So that's 12 factorial, and 12 factorial is 479001600. So 479,001,600 different ways to organize the songs on this list. And this is one of the interesting things about counting techniques, is they get big really, really fast. Okay. So now we can combine all these kind of ideas together and do some other counting techniques. So how many different license plate numbers can be made by using one letter followed by 5 digits selected from the digits 0 to 9? Okay, so what do we have? We have a letter, right? So that's A to Z. And then we have 5 numbers, 5 digits that are all 0 to 9. So how many choices do we have for the letter? Well, for the letter, there are 26 letters in the English alphabet. So we have 26 options. And then for each one of these digits, there are 10 numbers from 0 to 9, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 options for each of these. So those are 10 different things we have to do. And so then we can use the multiplication rule and multiply them together. And so we get 26 followed by 5 zeros, which is 2,600,000 different license plates. Okay, so that's the idea of what we're looking at here. So companies whose stocks are listed on the NASDAQ Stock Exchange have their company name represented by either 4 or 5 letters. Repetition of letters is allowed. What is the maximum number of companies that can be listed on the NASDAQ? Okay, So if we're doing the same thing over and over again, so we're picking 26 letters 4 times, right? That would be 26 times 26 times 26 times 26. So that would be 26 to the 4th power. So just like when we were doing the multiplication rule, if we want to do the same thing over and over and over again, we just multiply. We just raise it to the power of the number of times we want to do this. So this would be 26 to the 4th plus 26 to the 5th. And the reason we use plus is because of this word or, right? Back when we were doing the general we were doing the addition rule, we said the word or goes with addition. And in this case, we don't need to do any subtraction because there's no overlap between 4 and 5 letter combinations. So this is just 26 to the 4th plus 26 to the 5th, which is 1, 2, 3, 3, 8, 3, 5, 2. So that's 12,338,352 different combinations. Okay. Next one. A social security number is used to identify each resident of the United States uniquely. The number is of the form 3 numbers, 2 numbers, 4 numbers, where each X is a digit 0 to 9. So there, for each one of these X's, there are 10 options, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9 digits total. So this would just be 10 to the 9th power. So that's a 1 with 9 zeros after it. So there are 1 billion different social security numbers. What is the probability of correctly guessing the social security number of the President of the United States? Well, remember, this is just probability. So how many options are there for the social security number of the President of the United States? How many social security numbers does the President have? Well, they have 1. And then how many total options are there for social security numbers? A billion. So it's a 1 in a billion chance that you could correctly guess the President of the United States social security number. Okay. So at this point, what I'd like you all to do is pause the video and try these 4 problems, and then when you hit play, we'll go through them together. They're pretty similar to what we just did. Okay, so suppose that a local area network requires 8 letters for usernames. Lower and uppercase letters are considered the same. How many usernames are possible for the local area network? Okay, so you're doing the same thing each time. You have to pick 8 letters. They can be any letter you want. So you want to pick out of 26 things 8 times. So that's 26 to the 8th power, which is 2.088 times 10 to the 11th power. Okay. Companies whose stocks are listed on the New York Stock Exchange have their company name represented by either 1, 2, or 3 letters. Repetition of letters is allowed. What is the maximum number of companies that can be listed? So you could either have a 1-letter name. There are 26 options for that. You could have a 2-letter name. There are 26 squared options for that because repetition is allowed. If repetition wasn't allowed, then this would be 26 times 25, right? Because you and we'll talk more about repetition not being allowed here in a minute. But you'd have 26 options for the first letter, and then you couldn't use that first letter again, so you'd only have 25 options for the second letter. And then for the third letter, it would for a 3-letter one, it would be 26 to the 3rd. And so that's 18,278 different combinations. And then the last one, outside of home, there's a keypad that will open the garage if the correct 4-digit code is entered. How many codes are possible? Well, each number has 10 options, and you're going to do 4 of them, so it's 10 to the 4th power, which is 10,000. And the probability of correctly guessing it would be 1, because there's 1 correct code over the 10,000 possible codes. Okay, so that's the basic idea of the multiplication rule. Now what we want to get into more is this, and where all of these are examples where repetition is allowed. When repetition is allowed, you're going to use the exponent to say I'm going to do this same thing this many times. But the question becomes, what do I do if I don't want repetition to be allowed? So let's look at that. So that's where things called permutations and combinations come into play. So a permutation is an ordered arrangement in which R objects are chosen from n distinct different objects and repetition is not allowed. the symbol lowercase n, p, lowercase subscript r represents the number of permutations of r objects selected from n objects. For something to be a permutation, there are three keys. The objects have to be distinct, so you have to be able to tell them apart. You're not allowed to do repetition, and the order does matter. So to give you an example of this, let's say my three things are, let's just say I have three things. So n is 3, and let's say those three things are A, B, and C. And let's say I want to pick two of them. Okay? So then what I'm trying to do is I'm trying to find every combination of two objects out of these three objects, and how many of those are there. So for example, I could have A with B. I could have A with C. I could have B with A, and I could have B with C, and I could have C and A and C and B. And so I end up with 6 total options because order is important. So these two, AB and BA, are different. Okay, so that's the idea of what we're talking about when we're doing permutations. And the formula for this is n factorial divided by n minus r factorial. Okay, so we already kind of know, if I go back to this example we just did, one way I could try and do this is I know I have two choices, right, to make. For the first choice, I have 3 options, A, B, or C. But for the second one, I only have 2 options because I chose one of them already. So that's 3 times 2, right? And the way the formula works, if I look at this example, is this would be 7 factorial over 7 minus 2 factorial. So that's 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 factorial, which is 5 times 4 times 3 times 2 times 1. And notice what our goal here is, if I have 7 things and I want to pick 2 of them, one way to think about that is, well, I have 7 options for the first choice, and then I have 6 options for the second choice. So it would be 7 times 6 is what I should get for my answer. And that's what this formula does, right? Because 5 divided by 5 is 1, 4 divided by 4 is 1, 3 divided by 3 is 1, 2 divided by 2 is 1, and 1 divided by 1 is 1. So we just end up with 7 times 6. Okay, which is what we would expect to happen, right? So we end up with 42 options when we use the formula. So basically what the permutation formula does is it writes out factorial for 7 all the way down to 1, and then it cancels out all the numbers you don't want beyond those first few. We also can use our, so this is my preferred method for doing a permutation. If I tell you to do 7p2, that just means multiply the first 2 numbers of the factorial of 7. In this case, 7 times 6. If I told you to do, I'm going to just add another one in here. Well, let's just do this next one. If I told you to do 5p5, that just means multiply the first 5 numbers of the factorial. So that's 5 times 4 times 3 times 2 times 1. In this case, that's the entire factorial. Okay, right? The entire factorial. So that one's actually 5 factorial. And if we look at the formula, what happens here to give us that 5 factorial is it's 5 factorial over 5 minus 5 factorial. 5 minus 5 factorial is 0 factorial. And remember, we said 0 factorial is 1. So that is indeed 5 factorial. Okay. But this is the way I like to do it unless I'm dealing with really big numbers. I would just write out the first so many factorial. So in that case, 5 factorial is 120. So likewise, if I was doing this one, 9p4 simply means do the first 4 numbers of the 9 factorial. So that's 9 times 8 times 7 times 6, right? Those are the first 4 numbers of the 9 factorial. That's pretty easy to type into a calculator, right? Let's just go ahead and try that. Right, 9 times 8 times 7 times 6, right? So that's 3,024. Or you could use the formula. So the formula is under stat, And there it is, right? NPR. And then it's going to ask you to write this in an interesting way, which is you want to put in the N comma the R. So this would be 9 comma 4, which as you can see is 3024. So in our calculator, so when I put this in my calculator, it is NPR, and then you're going to put in 9 comma 4, like that. If you're using if you're using class count. Okay. So you're going to use this permutation formula anytime you're selecting from a group of things, a portion of that group, and the order in which you select them matters. So let's look at some examples where that would be the case. So like, for example, 4 members from a 20-person committee are to be selected randomly to serve as chairperson, vice chairperson, secretary, and treasurer. The first person selected is the chairperson, the second vice chairperson, third secretary, and fourth the treasurer. How many different leadership structures are possible? So first of all, you're talking about people, so they are distinct. So that's check 1 on yes, we want to use a permutation. 2, is repetition allowed? No, because you cannot be 2 or more of these positions at once. You only get to be 1, so we can't repeat people. And last but not least, is the order important? Yes, in this case, the order is important because when you are selected, it tells us what position you have. Okay, so this should be, there are 20 people total, and we want to pick 4 of them. So that should be 20P4, which you can do as 20, do the first 4 of the permutation here. So 20, 19, 18, 17. Or you can use the formula. So if I bring my calculator back up, as a formula, it would be I choose NPR, and then I put in 20, and then I put in 4. And there it is. It's 116,280 different possible options for this committee. Okay. Similarly, the second one here is also a permutation. So suppose 40 cars started the Indianapolis 500. In how many ways can the top 3 cars finish the race? Okay, so this is a permutation because the cars are distinct. They're different, so they are distinct. You can't finish first and third. Okay, so repetition is not allowed, and the order does matter, right? Because finishing first is different than finishing third. So this should be 40P3. Okay, and so we can put that in our calculator. So I can stat NPR, and I can do 40P3. Okay, and that's 59,280. Or I could also do, as we discussed previously, this would also work as 40 times 39 times 38, and it would give you exactly the same answer. Okay, so go ahead and pause the video for a moment now and try these other 2. First, make sure you understand why they are permutations, and then go ahead and do the permutation calculation. Okay, so now that you've had a chance to try these, let's talk about them. So a lottery exists where balls numbered 1 to 25 are placed in an urn. To win, you must match the 4 balls chosen in the correct order. How many possible outcomes are there for this game? So the balls are numbered, so they're distinct. Order is not allowed because repetition is not allowed. Okay, and then you have to guess them in the correct order. So that's why this is a permutation. So this would be 25P4, which is just going to be 25 times 24 times 23 times 22. Which is 303,600. Then last but not least, how many ways can the top 2 horses finish in a 10-horse race? So that's really similar to the race car one above. So it is a permutation. So this should just be 10 times 9, which is 90. Okay, so that's the idea for permutations. So now what we're going to do is we're going to look at the same idea except where order doesn't matter. The order is not important. And these are called combinations. So a combination is a collection without regard to order of n distinct objects without repetition. The symbol is NCR. So both of these, a combination and a permutation, have these first 2 things in common. N objects are distinct. the order repetition is not allowed. The thing that makes a combination different is that order is not important. So these are for situations where you just want to pick, like, how many different ways can you pick any 3 names out of a hat? Okay. If you don't care what order they come out of the hat, then this would be a combination instead of a permutation. And the formula for this one is, well, let's go back for a second to my picture here. If I did, well, here, I'll just rewrite it. So if we did exactly the same thing as we did before, so we want n to be 3, and we want to pick 2 of them. So we've got A, B, and C. So my pairings that I had before were AB and AC, BA and BC, and CA and CB. But now with a combination, I don't care what order it is. So these two, AB and BA, are the same. So we have to get rid of that one. AC and CA are the same. So I want to get rid of that one. And BC and CB are the same. So I want to get rid of that one. So now I'm only left with 3 options. And so what we have to do is we have to get rid of the repetitions. How many repetitions of each possible combination would there be? So the formula for this one is n factorial over n minus r factorial, right? So that's the normal permutation. But then we want to get rid of any repetition. So we're going to multiply that by r factorial. So notice here, every combination showed up twice. A, B, B, A. A, C, C, A. B, C, C, B. That is 2 factorial. 2 factorial is 1. Okay? And so we needed to get rid of all those duplications. Now, in this case, using the calculator is actually probably simpler than trying to do this by hand. Okay? So if I want to do 7C2, which is the first one, I'm going to do stat NCR, and I'm going to put in my 7 and my 2. You definitely don't want to use the formula, and there's no real shortcut here to do this one. So that first one was 21. Okay, the second one, how many ways are there to pick 5 things? And out of 5, when you don't care what order they come out of? Well, that's just 1. Okay, because if you don't care what order they come in and you're picking 5 things, everybody gets picked. There's only one way to do that. And then the last one, 9C4, stat, NC4, 9C4. And that's 126. So notice all of these are less than what we got 2 pages back. Okay? And that should make some sense because in this case, the repetition doesn't matter. So you don't, the order doesn't matter. So you're going to get a lot less options because A, B, and BA are considered the same here, so they don't get counted twice. So let's look at some examples that fit this description. Okay, so how many different simple random samples of size 7 can we obtain from a population whose size is 100? So here's one example. How many different simple random samples you can get is a combination because all I care about is are you in the sample or not. So that would be 100 C7. Okay, so stat NCR 100 C7. And it is a lot, right? That's what we see there. It's 1.601 times 10 to the 10th. So there are a lot of different simple random samples of size 7. Okay. Another example would be in the U.S. Senate, there are 21 members of the Committee on Banking, Housing, and Urban Affairs. 9 of these 21 members are selected to be on a subcommittee on economic policy. How many different committee structures are possible in the subcommittee? So once again, all that they're asking is how many different ways are there to get a subcommittee. So all that matters is that you're on the subcommittee, not when you got on the subcommittee. So this one would just be 21C7, right? We're picking 9. 21C9. We're picking 9 out of 21. Okay. And there you go. There would be 293,930 different committees. And then the last one here would be just like the one we did at the top. Okay, so that's combinations and permutations, and they're different. So the only difference between these two is whether or not the order in which they're selected matters. If the order doesn't matter, it's a combination. If the order in which they're selected does matter, it's a permutation. Okay. So there's a couple more things, and then we'll be done. So there's one more formula here, and then we're going to look at using these counting techniques to do probability problems. So what if the objects aren't distinct, but we want to do permutations? So that's what this formula is. So the number of permutations of n objects where n sub 1 are of one kind, n sub 2 are of a second sign, and so on, looks like this. N factorial over n sub 1 factorial times n sub 2 factorial dot 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 n sub k factorial. So basically what we do is we assume they're distinct, and then we, sorry, I don't have this up on the screen. So here's the formula. So basically what we're doing here is we're assuming they are distinct, and then we're dividing out the repetitions. Okay? So for example, if we look at this first example here, how many distinguishable DNA sequences can be formed using 3 A's, 2 C's, 2 G's, and 3 T's? So one way to write that, I'll just write it the simplest way, which is AA, A, T, T, oh, whoops. Except I didn't write it the simplest way. C, C, G, G, T, T, T. Okay? So there's one way to write that. If these were all distinct, if they were the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and order matters, then flipping the first two numbers would change it, right? Here, right, because then it would be 2, 1, 3, 4, 5, 6, 7, 8, 9, 10. And if order matters, those two are different. Whereas over here, if I flip the first two, nothing changed. So that's the same, so I don't want to count it. And that's what's going on here. What we're doing is we're taking the total number of different combinations and dividing away the repetitions. So in this case, we'd have 3 plus 2 plus 2 plus 3 is 10. So 10 factorial divided by 3 factorial times 2 factorial times 2 factorial times 3 factorial. Okay, so we're getting rid of all the combinations where we just switch around the A's. That's this 3 factorial and so on. So we can just put that in our calculator. So it's 10 factorial divided by, and then you could use some things to do. 3 factorial is just 3 times 2 times 1. But one question is, did I even really need the 1? And the answer is no, right? Because times 1 doesn't do anything. So times 2 factorial, so that's just times 2. Times 2 factorial again, times 3 factorial, which is 3 times 2. So that would be 25,200 different combinations of those DNA sequences. Okay. So this next one is similar, right? A golf course architect has 4 linden trees, 5 white birch trees, 2 bald cypress trees, and to plant on in a row along a fairway. In how many ways can the landscaper plant the trees in a row, assuming that the trees are evenly spaced? So it's the same idea, right? I've got 4 of something, 5 of something, and 2 of something. They're all considered different. So we take the total number of things, which is 4 plus 5 plus 2 is 11. So 11 factorial, and then we divide by the factorial of each type. Okay, so 11, whoops. 11 factorial divided by, and then you could do this one of 2 ways. I could use the factorial symbol, or I could do 4 times 3 times 2 times 5 times 4 times 3 times 2 times 2, right, to do that by hand, and we end up with 6,930. So even though we have more total things, we get less options because our things are repeated more. So that gets more options. Okay, so at this point, pause the video and try these last 2. Okay, so this first one, we've got 1A, 4 C's, that's 5, plus 3 G's is 8, plus 4 T's is 12. So 12 factorial divided by 1 factorial times 4 factorial times 3 factorial times 4 factorial. And so when I do that, I get 138,600 distinguishable DNA sequences. And then for the last one, you've got 9 total things over 3 factorial times 4 factorial times 1 factorial times 1 factorial. Which is 2,520 different lineups. Okay, so that was the last of our, whoops, sorry, I didn't put these up here. So here's the actual answers and written out, so I'll pause for a second. Sorry, I forgot to switch back screens. Okay, so now that we've looked at all these different counting techniques, let's look at using them to do some probability problems. So the first one here says, in Mega Millions, an urn contains balls numbered 1 to 56, and a second urn contains balls numbered 1 to 46. From the first urn, 5 balls are chosen randomly without replacement and without regard to order. From the second urn, 1 ball is chosen randomly. For a $1 bet, a player chooses 1 set of 5 numbers to match the balls selected from the first urn and 1 number to match the balls selected from the second urn. To win, all 6 numbers must match. That is, the player must match the first 5 balls selected from the first urn and the single ball selected from the second urn. What is the probability of winning Mega Millions with a single ticket? Okay, so we're doing a probability problem. So to do the probability of winning here, right, that's going to be the number of ways to win divided by the number of ways to play. Okay? So the number of ways to win should be pretty straightforward, right? There's only one winning number, so there's one way to do that. The number of ways to play gets into our counting techniques. So it says from the front, the 5 balls are chosen at random from the first urn without replacement and without regard to order. Well, without replacement and without regard to order is a combination. So that means we have 56 options, and we want to choose 5 of them. And then we have to choose 1 ball out of the other urn. Those balls go from 1 to 46. So how many options do we have? We have 46. And we can just use the multiplication rule to multiply those together, right, to see how many we get total. So we do 56, we're doing a combination, and then we put in 56, comma 5, and then we're going to multiply that by 46. What we end up with is 175,711,536. So 175,711,536 different options. And so our probability is just 1 out of that many, which is pretty low odds. And this is right on how this works. So if you were to play Mega Millions, this is your odds of winning. So that's 5.7 times 10 to the negative 9th. Okay, so that would be that's 0.00000 1, 2, 3, 4, 5, 6, 7, 8, 9. So 7 probability, which is 0.0000000. Oops, I put 1 too many zeros. 57% chance of winning. So you've got a fairly low chance of winning. Okay, so let's try another one. Suppose there are 55 Democrats and 45 Republicans in the U.S. Senate. A committee of 7 senators is to be formed by selecting the members of the Senate randomly. What is the probability that the committee is composed of all all Democrats? Okay, so we need to do the same idea. So the probability of all Dems is the number of ways to select all Dems divided by the total number of ways to select the committee. Okay? So the number of ways to select all Dems, so you've got 55 things you want to choose. You've got 55 Democrats. You want to choose 7 of them, right? You cannot repeat them. because you can't have the same person on the committee twice. And the order you select them doesn't matter. So this is another combination. So this would be the number of way to get all Dems would be 55C7. And then the number of committees total would be 100C7. So here, let me go ahead and just do at least one of these with the calculator up here to remind you what it looks like. So stat, we choose NCR, 55, 7 is 202927725. And looking back at this, it's probably going to be better just to put this all in my calculator at once. So instead of doing what I just did there, go ahead and now divide it by another NCR of 100, 7. Okay, and that'll give you the probability. So the probability of it being all Democrats would be 0.0127, which is about a 1% chance of that happening. Okay. What is the okay, so that's what we got there. What is the probability that the committee is all composed of all Republicans? So it's the same idea. The probability of all Republicans is the number of ways to get all Republicans divided by the number of ways to get the committees. So the bottom isn't going to change. It's still going to be 100C7, but on top, it's going to be 45C7 because we only have 45 Republicans. And then you put that in the calculator exactly the same way, and you would expect a probability that is slightly smaller than the one we just got, because there should be less ways, and it is a little smaller. It's 0.0028. So it's less than 1%, whereas that one was a little bit over 1%. They're about 1% difference. And then the last one here says, what is the probability that the committee is composed of 3 Democrats and 4 Republicans? So the probability of all, the probability of 3 Dems and 4 Republicans. Okay, so what that means is we're going to need to get the number of ways to get 3 Dems, and we're going to multiply it by the number of ways to get 4 Republicans, right? Because the word "and" tells us to multiply, and then we're going to divide again by the number of ways to get this committee in general. So that's going to be 55C3 times 45C4 over 100C7. Okay, so this one's a little more complicated, so let me show you how to put this one in the calculator. So I'd start by getting my fraction bar, and then I'm going to get C, so 55C3, and then I'm going to do times, and then I'm going to go in here to stat again and choose NCR again, and do 45C4. Then on the bottom, click to the bottom, and I'm going to put in NCR again, 100C7. And there's about a 24% chance of that happening. Okay, so that's the idea. So what I'd like y'all to do now is flip over to the next page and try these. Okay, so try these problems here. So pause the video and then we'll go over it. Okay, so now that you've had a chance to try them, let's go through them together. So in the Illinois Lottery game Little Lotto, an urn contains balls numbered 1 to 39. From this urn, 5 balls are chosen randomly without replacement. For a $1 bet, a player chooses one set of 5 numbers. To win, all 5 numbers must match the chosen from the urn. The order in which the balls are selected does not matter. What is the probability of winning Little Lotto? So this is really similar to the one we just did. So it'd be there's one way to win over, in this case, 39C5 ways to play. So that'd be 1 over 575,757, and then you could do that division. So 1 divided by that is 0.0000002. chance of winning. So a better chance than winning Mega Millions, but still not great. Okay? Then the next one. Suppose a compact disc you just purchased has 13 tracks. This is similar to a problem we did before, except you're going to listen to 4 songs. So this was in a previous section. What's the probability that you like 2 of them? Okay, so the first thing you want to notice here is if you like 2 of them, what else has to happen? Well, you have to dislike 2 of them, right? So this is very similar to the Senator's problem. So how many ways are there to like 2 songs? Well, you like 5 of them. You want to choose 2 of those 5, so that would be 5C2. Okay? Then you want to multiply that by the number of ways to dislike 2 songs. Well, if you like 5 songs, that means you dislike 8 songs because there's 13 total, so that would be 8C2. And then you want to know how many ways are there to play 4 songs out of 13 total, so that's 13C4. Okay, so then I'll just put that in my calculator. Let's go ahead. I'll do it here. So it's going to be very similar to this one we just did here. So I'm going to put in my fraction, and then I'm going to do 5C2. And then I'm going to do times. I'm going to go into my stat again. And then this time I'm going to do 8C2. Then on the bottom, I'm going to put in NCR, and I'm going to choose 13, 4. Okay, and so there's a 0.3916 chance that you would dislike 2 of them. Then the second one, similar idea. If you're going to like 3 of them, then you have to dislike 1. So we just need to change up some of these things. You need to like 3 of them, so that's 5C3 times 8C1 over 13C4 because you're still choosing 4 of them. Little trick to using this calculator. If you double click, hopefully, on what you put in before, you can bring it down and then you can just change the numbers in here. So I just need to change that 2 to a 3 and this 2 to a 1. And then I get 0.1119. And then last but not least, you like all 4 of them. So if you're going to like all 4 of them, then you're not going to dislike any. So that would be 5C4 times 8C0. Over 13C4. But if you're not going to dislike any of them, you can just get rid of that part. Okay, so this one, let me save that. This one, get rid of this second, and then just put in a 4 instead of a 3. And then you get 0.0070 when you round to the 4th decimal place. Okay, so that's it for this section. Interesting. Well, let me change back to my other camera, which is what I would normally do here, but I'll just finish off here. So that's it for today. Sorry, it's just playing around with stuff. So I'll just bring up a new movie recording here real quick, and then you guys can all see me to finish off. So that's the end of this video section for today. Thanks for watching. We've got one more section left in Chapter 5 where we're just going to put this all together and talk about choosing the right methods, because so far they've kind of been grouped by section, so we want to make sure you know how to pick the right method for doing this. Make sure you continue to do all your homework assignments, and feel free to send me any remind messages or emails if you have any questions throughout the week.